Assalamualaikum. So guys, we are moving to lecture number 6 in week 3. So in this lecture, I will show you how can we use the radioactivity to find out the age of the sample, which is called the radioactive dating process. So in the previous lectures, we have already learned about the radioactive decay as shown in the figure. So after first half-life, the half of the parent nuclei are converted into the daughter nuclei, and in the second half-life you have half of the nuclei of the last one, and then so on. So on the right hand side, the radioactive decay law is showing, and also the half-life formula. So we can estimate the age of the radioactive material using this simple formula. So by definition, it is a technique which is used to date main materials such as rocks or carbon-based materials, in which trace radioactive impurities were selectively incorporated when they were formed. So we can find out the age of the sample by measuring its radioactivity. As the radioactive half-life of a given radioisotope of course, is not affected by temperature, physical, chemical state, or any other influence of the environment outside the nucleus, save direct particle interactions with the nucleus. Therefore, radioactive samples continue to decay at a predictable rate and can be used as a clock because they are not affected by physical, chemical state, temperature, or other environmental effects. This makes several types of radioactive dating feasible. For geological dating, where the time span is on the order of age of Earth, and the methods use the clocks in the rocks, there are two main uncertainties, of course, in this data process. First one, what was the amount of daughter element when the rocks were formed? This is the one question. Second one, have any of the parent or daughter atoms been added or removed during the process? So this is the second possibility. So we can divide this process in usually two cases. Case one, when we are starting with simplest case, that there are no daughter atoms present at time t0 and no mass is lost from the sample. The age can be determined by measuring the relative amounts of isotopes. So at time t naught, here t0, there are np at t naught are the parent nuclei. So np are the parent nuclei, t naught at time t0. At time t1, we have npt1 parent nuclei with additionally ndt1 daughter nuclei, which are decayed nuclei. From equation 1, we can understand that at the time, and on the right hand side we have total number of parent nuclei at time t0, and we have no daughter nuclei at time t0. At time t1, we have both kinds of nuclei, parent nuclei and daughter nuclei, npt1 plus ndt1. Using the radioactive decay law, which is shown in equation 2, we can use this radioactive decay law to find the n number of parent nuclei at t1. So from equation 2, we can write the exponential, and by taking a log on the both sides, we end up with the second equation. And if we can solve this above second term, we can find out the delta t by just uh, a simple calculation, and this delta t is the time difference, t1 minus t0, and now we have the time elapsed in the calculation form, and after and dividing np t1 over np t1, we have a 1 and we have equation number 4. So if we know about number of daughter nuclei at time t1 and the number of parent nuclei at time t1 or their ratio, and this integration constant by experiment, we can find the age of the sample. So second is the case when we have daughter nuclei also present at initial time t0. You can see in the equation number 1, now we have added nd t0, which were missing in the last case 1, which means the number of daughter nuclei at time t0. So at time t0 we have both nuclei, parent nuclei and the daughter nuclei, and these are equal to npt1 plus ndt1. So here is the assumption that there are some nuclei of daughter nucleus which remained undecayed at time t1, and these are equal in number. So by using the radioactive, which is shown in equation, by using the radioactive decay law, and after dividing equation 1 by equation 2, we end up with the equation 3. So just by rearranging, we end up with this above term, and using the relation by which comes from the radioactive decay law, just putting this npt0 in the above relation, we end up with the third term, and after taking some constant out of first two terms, we end up with the desired equation. You can see, and this equation is similar to a straight line. So, and the thing we want to determine is the t1 minus t0, the time elapsed, the age of the sample. If we compare this elapsed equation, desired equation, with just the straight line, we can see that x is the npt1 over nd prime t1, and y is ndt1 over nd prime t1, and the slope m is equal to exponential minus 1, and the c is the constant. So if we know these ratios, nd t1 over nd prime t1, y and x np t1 over nd prime t1, we can plot a straight line which is shown for one of the example, and we can find the slope of the this curve which is plotted between y and x, and this slope of line will give us, of course it will give us some number, and from this slope, after rearranging, we can find the time elapsed. So here is the example of some samples for which we can find the age of the sample by using this relation, and I hope that you will do it by yourself also. So for reference, I recommend you to read your book in detail.